Hi, I'm Chris. I'm one of the electron microscopy technicians here in Cardiff. Today I'm going to be showing you how we would use an SEM to image your gold nanoparticles that you've synthesized during your course. This is the machine that we'll use, so let's go. Okay, so this is the TestScan Mirror 3 field emission scanning electron microscope. This is the machine that we'll be using to image your samples. The electron beam is generated about here in the column. It comes down the column, hits your samples in the chamber, generates a signal for us to look at. Because we're going to be doing such high magnification work, we actually need to turn off the lights because the EMF from the lights will introduce vibration into the image. So let's do that. Secondly, mobile phones, same thing. They need to come over here on the bench so we don't have any interference. So now we're ready to start imaging. Let's go. To load the samples in the chamber, we have vented the chamber and we can open the chamber like this. Okay, and now we can see inside the microscope. And right before us is the stage where we will be putting the sample. So the sample is here on this stub. And on this stub we have 3 sizes of gold nanoparticles. Let's load the sample into the microscope so we can get on with imaging. You'll notice that I'm wearing gloves. This is to keep the microscope clean of the grease from my fingers so we don't contaminate the sample and the microscope. I've secured the sample on the stage so it doesn't fall off and there's no excess vibration. So let's bring the sample underneath where the beam would be. The beam comes out of the bottom of the column here. Okay, and we need to bring the sample underneath. So let's home the stage. While the stage is homing, let's have a look at some of the detectors we have on this microscope. We have the secondary electron detector up in the back corner over here. And this generates the normal SEM images that you would normally see published everywhere on the internet. Just a typical SEM image. This one here is a backscatter detector, which is good for determining elemental contrast in your sample. And this one here is the variable pressure detector, or the VP detector, low vacuum detector, and it's good for charging samples, where you can introduce a small amount of gas into the chamber, and it will countercharge your sample. So let's close the chamber and pump it down. Now that we have the sample in the chamber, we need to make vacuum. Okay, we need to make vacuum because we're using an electron beam of high energy electrons to image our sample. Electrons and air make lightning, which is analytically useless. So let's pump down the chamber. To do that, we press this button in the bottom corner. Start the pumping. While the chamber is pumping, we need to do a couple of things. We need to move the sample into position, and we need to set the conditions of the microscope. So let's move the sample into position. We come here and we change the Z from 90 to, let's start by changing it to 10. And while the stage is coming up, we'll change the high voltage from 15 to 5 kV. Press the OK button. Change the beam intensity from 13 to 8, which will give us near optimum resolution for the microscope. Beam intensity is just an arbitrary measure of the beam current that we're using to image the sample. The sample's in position. We have to wait for the chamber to pump down. It's about a 3-minute pump time to reach vacuum. Now we've achieved vacuum, let's go ahead and turn on the beam and start imaging. So the image of the electron beam comes up here on our screen. Also, the brightness and contrast is way out. I can't actually see anything at the moment. So let's get the microscope to do some work for us and do some auto brightness contrast. Much better. Let's increase our mag a little bit like this and focus. Okay. Believe it or not, that image is actually in focus. It looks pretty blurry. That's because I haven't done any alignments at all on the microscope. We'll do that once the stage is in its final analytical position. Okay, let's have a look at what we've got. We've got our 3 TEM grids, 1, 2, and 3. So we're going to have to do some exploring of our samples to find the nanoparticles and work out which ones are which. So now that I've focused on the sample, we're going to use the focal distance, which is pretty accurate from the microscope, much more accurate than the stage position. We're going to use that focal distance, and we're going to move the stage into its final analytical position. To do that, we come up here to the working distance and Z function on the stage control, and we're going to type in 3.5. And you'll see the sample raise up closer to the microscope. What you'll also notice here is that now our image has gotten dark. And it's dark because the collection efficiency of the secondary electron detector has dropped off as we get the sample closer to the pole piece, or the place where the electrons come out of the column. All right, so we're going to swap detectors from the secondary electron detector to the in-beam SE detector, or secondary electron detector, and I have a much nicer, less grainy image, much more signal. Now that we're in our final position, we're going to turn on the beam deceleration mode. And basically what this does is it adds an extra 5 kV to the gun, sends it down the column at 10 kV, and we're after 5 kV landing energy, which means that we need a negative 5 kV charge on the stage. This will slow down the beam as it hits the stage and give me a 5 kV landing energy. The reason why we do this is because the beam comes down the column in a much more coherent, higher resolution manner at 10 kV than it does at 5 kV. And then we can apply the brakes at the stage, and we get a 10 kV resolution beam at a 5 kV signal. And it looks a bit different. And we'll just focus on the sample. Now it's in position. There we go. We'll do our brightness and contrast. And the last thing that we're going to do is, now that we're in focus, is we're going to set our spot size. And we're going to set our spot size to 0. What this tells the microscope is that I want the highest resolution image possible. Doesn't seem like much of a change, but here we are, and we can see that we have a much better image, increased resolution, and we're now imaging at 400,000 times already. So the next step is to align the microscope, to get rid of all this fuzziness, to give us a nice sharp image. Okay? There are 2 things that we need to do for this. We need to align the beam down the column, and we need to make the beam circular. So the wobbler for aligning the beam, and the stigmators for making the beam circular. So we're going to start by aligning the microscope with the wobbler. It doesn't matter if you do the stigmators or the wobbler first, but I like to do the wobbler first because that affects the stigmator. First of all, let's drop the magnification to something reasonable. Let's say 100,000 times. Let's turn the wobbler on with this button here. Brings up the wizard. So basically what the microscope is doing at the moment is it's taking, this is our focal plane, and it's moving it up and down, above and below focus, okay? And what this does is it tells me if the beam is aligned down the column. If it's not centered down the column, the focal point will move as it moves up and down. It'll move laterally as it moves up and down as well. Okay, so to align the beam, all I have to do is stop the movement in this image. And you can see that I have an X and Y component to this image. At the moment, the Y component is much worse than the X component, or much larger movement. So we're going to correct for the Y direction first. Okay, we just do that by rolling the ball in the Y direction. It's worse. Okay, and we do this in an iterative fashion, so we're going to correct for the X now that we've mostly fixed the Y. This can be quite fiddly and can take quite a fair bit of time to do. And we can see there's a little bit of carbon contamination in the beam as well, or coming underneath the beam, because this area has turned black. So let's just move across an area or 2, and now we can actually have a nice area to look at. And that's probably still a little bit too much, eh? Okay. So once we're happy with what we've got, we can click the finish button, and that will turn the wobbler off. I'm happy with the wobble. Let's increase magnification and do some focusing and see what we got. As I focus, as I take the microscope above and below focus, the focal point is here. If I go this way, it starts streaking in this direction. If I go this way, it starts, go back the other way, it starts streaking in this direction. Okay, this is because the beam is not round. Okay, we have an elliptical beam, and as we go through focus, we're taking an ellipse from this to this. Okay, so let's correct that. We use the stigmators to correct that. We can come up here to the stigmators. Okay, and we'll correct them using the ball. You can see that now, as I adjust the focus, instead of stretching or pulling, it's actually just going blurry. Okay, So there we have the corrected beam. So when I take an image on the SEM, I will focus and stigmate at twice the magnification I want to take the image at. I will come back to half the magnification and take the image. The maximum magnification of this microscope is 1,000,000 times. So we'll be imaging it 500,000 times, 600,000 times, if we're lucky. Okay, so now that we have the basic alignment in place, let's go find some nanoparticles, some more nanoparticles. To look for them on the sample, let's decrease our scan speed a little bit so we can see what's going on. I think I can see a cluster just here. Okay, these are our gold nanoparticles. So let's increase our magnification and focus fully and do our final alignments. Okay, 1,000,000 times, we're at the top. Okay, let's adjust our stigmators to make sure that we're happy with that. What you can see here on the screen, as I'm talking, you can see the sound my voice is making affecting the image. So as I talk, it vibrates. Let's do the stigmators. Stigmate. I'm pretty happy with the wobbler. I can tell as I've changed the focus that the image isn't moving very much. So I'm happy with the wobbler, the column alignment, and so I'm just going to do a final adjustment on the stigmators to make sure I'm happy again. Okay, and then I will check it with focus. Not quite happy with that. Okay, I'm going to set my magnification. Let's go 400,000 times. That's 400,000 times. I'm going to hit the go button, and I'm going to hold my breath. Here's our nice image of gold nanoparticles. And these nanoparticles are anywhere between 20 and 30 nanometers in size. And we can measure them. So let's come up here to our measurement tool. Okay, oh, there it is. And we can measure them using this one. Measure them in a variety of ways. So let's measure the width of this particle. Parallel width from the side to side, 21, 22 nanometers. Let's measure this guy. 18 nanometers, 19 nanometers. Got some smaller ones down here. Let's measure this one. 17 nanometers. And this little fella down here. 15 nanometers. Okay, so we can set up measurements like that on our screen. And I can also just get rid of them as well. Okay, and then we can finally save our image. Save image. And here we have a nice saved image of your gold nanoparticles. I hope you've enjoyed this demonstration of how we can use SEM to image and characterize your particles. All the best with your reports, and I hope you enjoy getting your teeth into all the data that we've generated here at CARF for you.